In this problem video, we're going to take apart a fairly long worded question and really try to set it up and do well. Now, to that end, I'm going to ask you to pause in a moment and try to solve the entire thing. But if you do find that you're stuck with any of the pieces, hit play, listen until you get the piece that you need, and then pause it and try solving for the rest yourself. Now, let's start out with the problem. Calcium carbonate, given as CaCO3, which is a solid, decomposes upon heating to give calcium oxide, solid, and carbon dioxide, which is a gas. A sample of calcium carbonate is decomposed, and the carbon dioxide is collected in a 250 milliliter flask. After the decomposition is complete, the gas has a pressure of 1.3 atmospheres at a temperature of 31 degrees Celsius. How many moles of carbon dioxide gas were generated? Now, if you're trying to jump through this completely on your own, pause and try it now. If you wanted a little bit of guidance, here's the hint. Write your balanced chemical reaction. Figure out how many moles of gas you have initially, how many moles you're going to be generating, and then we're going to figure out how much extra gas we're producing over and above our ambient atmospheric pressure. So pause now if you needed to. Okay, so let's set this up. Now, remember that we're going to have PV equals nRT. I'm just going to park this down here so that you can refer to it at any point. Okay, so we're going to have to work this one through. Let's start out by listing out my variables like this. I always like to do this because it's the way that I can keep myself really nice and organized. So we were asked to find how many moles of gas were produced. So that's the thing I don't know. I always know my R. That's going to be 0.082. And I'll go one more sig fig on that, 1. And the units on that will be liters times atmospheres divided by moles times Kelvin. That reminds me of what I need to get into for each of my units that I'll have over here. Currently my pressure was given to me to be, 1.3 atmosphere. 1.3 atmosphere. So obviously I'm going to have to convert from atmosphere. Oh, no I don't. I'm already in atmospheres, so I'm in good shape there. Now volume, I'm obviously going to have to convert from 250 milliliters into liters. That one I will have to do. Now, I'll have 250, notice the decimal point communicating I have 3 sig figs, milliliters of gas initially. Let's see. Okay. And now we have our temperature, which is 31 degrees Celsius. 31 degrees Celsius. What we'll want to do now is we want to actually convert those into appropriate units for our ideal gas law. This is the easiest of them to do, I think. So let's just go ahead and set that one up. I've got 250 milliliters. I have 1,000 milliliters equaling 1 liter. Exact conversion, no impact on sig figs. I'm going to slide my decimal place over 3 times, so it'll be 0.250 liters. So we've got that information now. Next up, I need to go ahead and convert my temperature into Kelvin. So if I got 31 degrees Celsius, remember that Celsius and Kelvin are on the same scale. So the increments are the same size. What we have to account for is the 0 point. So for that, we're going to add 273 to it. So 31 plus 273.15 is going to give me, 304.15. Let me just clean that up. 304.15. Now we handle our sig figs. Remember that we're lining up at the decimal point and chopping off. There's nothing after the decimal point here, meaning that this will be chopped off. I'll have 304 Kelvin. We don't actually say degrees Kelvin if we're being really proper about it. We just say Kelvin, but you'll often hear people say degrees Kelvin just as a matter of habit. It's not quite proper, but it's tolerated. Okay, so we've got all of our pieces in place now. What we can do is we can either just plug it into the ideal gas law as written, or we can start rearranging the ideal gas law to solve for n. I'm going to go ahead and do it that way. So I have PV equals nRT, and I need to solve for the number of moles. I'm going to take R over to the other side by dividing it. I'm going to take that over to the other side by dividing it as well. So I end up having PV divided by RT equals N. Now we're going to go ahead and put things in. So we're going to have our pressure, which is 1.3 atmospheres. 1.3 atmospheres. And we're going to have that multiplied by 0.250 liters. That doesn't look too much like a 3. Let me fix that. There we are. That's better. We're going to have our 0.0821 liters atmospheres over moles Kelvin on the bottom. And then next up we're going to have our 304 Kelvin. Now let's handle everything on the bottom of the fraction first, because I'm going to cross cancel some units. Now since we're just down here on the bottom, there's nothing fancy I have to do. I say, hey look, this is on the bottom of a fraction, that's on the top of this area's fraction, so those will cross cancel. Now when I'm ready to actually try solving for it, I have to remember that fractions of a fraction, you have to invert and multiply, or if you prefer, we just take the fraction down here and we put it at the very top. Now looking here, I have atmospheres that'll cross cancel, liters will cross cancel. My unit would end up being 1 divided by 1 divided by moles, which is moles. So this will be in units of moles when I actually grab my calculator. Let's go ahead and grab that calculator right now. Okay, so we have 1.3 times 0.250 divided by 0.0821 divided by 304. Make sure that you remember that you're still dividing by down there on the bottom, because I see a lot of people type that in their calculator as a plus sign right here, as a time sign right there, and we don't want to accidentally screw up our whole calculation. We hit enter and we get this value coming off of it. So we're going to be at 0.013017 moles. Now we need to account for our sig figs. I've got 2 sig figs, 3 sig figs, 3 sig figs, and 3 sig figs. I'll have a total of 2 sig figs in my final answer. Final answer should be 0.013, 0.013, and will be in moles. That's how many moles of carbon dioxide gas we generated in the course of this reaction. Okay, and in fact, let me go ahead and put carbon dioxide there since I know it as well. And we want to always be as rigorous as we can in our final answers. There we go. So that'd be the final answer for this problem.